start this recording. We're actually going to record this webinar, so I think it's going to be made available to people later on after we're done. And right now what I'm going to do is mute all of your microphones. So I'm not trying to be rude or anything, but so that during the first part of the presentation for the 40 minutes, that just in case there's some serious noise or something, you know, when you're moving around, that won't be picked up. Like I said in the email that was sent out, after the presentation I'll be answering questions, and I'll unmute that so we can talk back and forth. But what I'd like to do is have you put your questions into the chat box. I think each one of you should be able to see the chat box there on the GoToMeeting panel that's been supplied. So if you could, when we're going through the material, when you think of questions, if you could just start putting them down there, maybe put your name, colon, and then put what your question is. And what I'll do is at the end, I'll be using that for my order on how I answer questions. So if there's something really urgent that you think needs to be, you know, talked about while I'm presenting, go ahead and just put that in the chat box, and, you know, and I can unmute the microphones, because there's 15 of us on right now, and we're expecting up to 25. So anyways, that's just the procedure we'll take. So let's get cruising now. What I'd like to do is first start off with the main purpose for having, and I'm going to put in a file here, or load the file in. And the main purpose is to create for ourselves a decrease in harmonic distortion due to some type of a load that we may have. Or what we also may want to be doing is applying power factor correction, and we want to avoid some type of a resonant condition when we apply that power factor correction. So that's the two most key things that we're going to be applying notch harmonic filtering for: avoidance and for reduction in distortion. One of the most critical things, obviously, in a notch harmonic filter is its tuning. Where do you tune it? Given the proliferation of 6-pulse drives and multi-pulse systems that we have out there, obviously the fifth harmonic is a key point that we're all very familiar with. But that's not necessarily the best place to be tuning at. Where you want to tune at is going to be what we'll consider your lowest characteristic harmonic of the particular loads or load that you're trying to reduce distortion with or to avoid resonance with. And for instance, in this case that I have up here, I've got just a quick EasyPower model of a system. I've got a 13.2 kV secondary on these two transformers. I've got a 115 kV primary. I've got a not a completely stiff source, but it's a 700 MVA short circuit level up here. And in this case, I have a fifth harmonic filter that I've tuned to the fifth harmonic. But over here, what I decided to do was, instead of putting a 6-pulse drive that obviously the fifth harmonic filter would work well with, I put an arc furnace load over here that could be characteristic of any number of type of arcing loads, which have a rather random or stochastic process in how they produce harmonic currents. In this case, this is an actual arc furnace in a melting condition with second, third, fourth, and fifth harmonic. If we were to double-click on this load symbol in EasyPower, going to the Harmonics tab, you would see that it's really 2, 3, 4, 5, and 7. That's all there is here. And when I was measuring this at an actual installation, these really were the predominant harmonics. Anything above this basically fell off very rapidly. In this condition, given that we have third, second, third, and fourth, what we'll find is applying a fifth harmonic filter may not really be the smartest idea. So if we were to enter the harmonics focus, we were to look at our distortion condition, we would see that where distortion on the voltage really isn't too high, but you know, we're interested in power factor correction of this load. If we go back to database focus, you notice it is 5 megavars. So I chose to do that. I chose to put a pretty poor power factor on this arcing furnace. And so going back into the harmonics focus, running a distortion, great, we're 3.7, we're fine, but we want a power factor, do some power factor correction. If we were to have designed this filter at the fifth harmonic, wow, that's not really a good condition. We basically increased our distortion up to 25%, and that's not a really good application. In this case, for this type of a load, you're going to find yourself having to filter very low and start very low to make sure you accommodate all of the harmonic characteristics here. Again, we probably start filtering at the lowest one, at the second, believe it or not. These arc furnaces are very interesting. The second, third, and fourth, they're all positive and negative sequence. It's the transformers feeding these are typically delta connected, and these harmonics just come manifesting right out of it. This is not similar. This is not very much in line with our 6-pulse characteristic harmonics of a drive, where the fifth is going to be negative sequence, 7 will be positive sequence. What happens is when you'll have thirds appear that actually happen to be positive and negative, and so they'll just blow right through transformers, and you're going to have to deal with them. So in this case, a fifth harmonic filter was a poor application, bringing the point home. You need to filter or begin your notch filter application at the point where your first harmonics are appearing. I've actually applied 11th harmonic filters on a system with an active front end, and in that case, they were producing no harmonics even upwards to around the 17th harmonic, when it was actually some form of a switching noise. So let's make sure that when we design notch filters that we properly specify. Now, the tuning point. Now, obviously, in this case, we can very quickly discern if we have the right spectral content that we made a mistake by having this high distortion level. Now, one of the key things that we're going to be using in all harmonic analysis is the driving point impedance scan. So let me close off this case, and I want to load a new case now. And let's see, let's load in this one, resonant effect. Now, again, this is pretty much that same system, but what I want to illustrate is that the driving point impedance is the point at which you're going to be looking up into the system to discern its harmonic character, and it differs depending on where you are. If we're on this main bus down here, let's go into harmonics focus, and let's assume that we don't have any harmonic filters on. So I'm going to open up these two breakers. In EasyPower Harmonics, of course, if you double-click on the bus, you get a driving point impedance scan. It defaults to being in per unit, which is convenient because we're going to be injecting 1 per unit current. So if we double-click on this bus, what we're going to see is a straight line ramp. And what this is saying is, as frequency increases from the 1st to the 21st harmonic, the impedance of the system is going up linearly, which is true because X sub L in the transformer is 2 pi FL, so it's a linear relationship between frequency. And in other words, it's a linear increase with frequency. Also, the driving point impedance of the utility up here is also pretty much inductive, and so because of that, we get that nice ramp. If we were to look at any location, we're going to see a ramp. Any one of these locations, we're going to see the driving point impedance is going to be a ramp. However, if we were to put, for instance, a fifth harmonic filter on here that's been tuned at the fifth harmonic, and we double-click at this bus, we get exactly what we would expect. We have a filter that has a first parallel resonant point. That's one of the issues with notch harmonic filters that we have to be careful of, and I have a couple notes on that I want to go over. We have our tuning point where it draws the system impedance down. Again, the whole idea behind a notch harmonic filter, and I might be preaching to the chorus a little, to the choir a little bit, and I understand, but I'm just going to go ahead and go over these things. The whole point is to draw the net impedance of the system down so that the harmonic currents choose to flow into the filter via current division rather than up to the through the utility transformer. So if we look here, when I double-clicked on this bus, it gave me the driving point impedance of everything on the bus, everything up here and down. Notice an interesting thing happens. If I double-click on the utility, it looks different. So what I have here, looking from the utility perspective down into this industrial system, I pretty much have the ramp interrupted a little bit by the filter down on the secondary bus. Now, what would happen if I had two harmonic filters on, two separate supply transformers? What would I get? The other filter on the other bus, looking up through the two transformers here. This transformer up and back down again is basically manifesting here. And so we have to be sure that when we're simulating our industrial systems, that we include every type of capacitive or filter component that might be involved somehow or linked into our system. So we can see that manifesting here. We can also see, if we double-clicked on the other bus, that it would manifest slightly differently. Now, the auto scaling kind of threw this up. It makes it look like it's a lot bigger. It's basically about the same resonant peak. The other auto scale jumped up to like 10, I believe, if we look over here. Yes, see, it jumped up to a scale factor of 10. So it went a little bit above 5, but these both have about the same characteristic with a little bit of a mirror image going on. So the point at which we are wanting to discern what the driving point impedance looks like, it really depends on where we are and where we're looking. And this brings up one of the key points that I want to drive home, and that is impedance buffering. If you're going to apply a notch filter of any form, you have to have some form of impedance buffering you from the rest of the system that you don't want to see your fifth harmonic filter. So in this case, I've got a utility grid up here, and who knows what might be up there? Who knows what type of distortion levels might be floating around? Now, in most cases, the utility bus voltage has fairly low distortion. I mean, probably 1–2% is very typical. But you would be surprised that if you created or presented a low impedance path to the utility system for like a fifth harmonic filter, for instance, you may get very surprised at how much current you absorb. When I worked back at Power Technologies in Schenectady, I worked under a guy named Ray Stratford. Many of you know who Ray is. He basically was the guy who was very instrumental in creating the IEEE 519 standard with a number of other people as well. He was one of the key players. And when I did my grunt work underneath him and I was cutting my teeth, he would tell the story of a utility applying a large fifth harmonic filter at a point in their grid because they had this issue and they wanted to, you know, kind of shunt off some of that fifth harmonic current. So they designed it. They designed what size the capacitors and the reactors would be for that filter. They put the thing online and it quickly exploded. And the reason why it exploded was very simple, that it absorbed every fifth harmonic current on the whole stinking utility grid for the around 100 or 200 miles. So a key item in notch harmonic filter application is going to be buffering. And here we have a clear, good reason that we can apply a filter down on this location. We may have, for instance, a load down here that we want to reduce the distortion going out through the transformer. In that case, we have this buffering impedance. And if we do a driving point impedance scan, truly, we do see, yes, the effect of the filter is minimized. And on top of it, where it's tuned and it resonates, those points are being shifted. And that's really important also if you're applying one over here. The effect of the other filter has been changed. It's modified as you're seeing it from this location. Let's do it another way. Let's unclick this filter, look at this bus, and whoops, that's that note right there. And again, we see the nice fifth harmonic filter. From this location, what do we get? Well, basically a ramp, and the impedance buffering now has kept the filter on that other bus from really manifesting for us on the bus where we're doing our impedance scan. Now, also, the driving point impedance, the stiffness of this utility source is helping us as well. So we have this buffering, and on top of it, we have a stiff connection up here helping to isolate these two systems. So buffering impedance, very, very critical and important for us. The next key item when you're looking at the notch harmonic filter is going to be capacitor duty. And John, it's really interesting that you're on here, and we had discussions about this just last week, how applying the capacitor standard 18. Now, if we go back to the database focus, and we look at the notch harmonic filter, which has been selected here, notice that we have two key components that we're looking at. We're going to be looking at the inline reactor, a series reactor, and a capacitor. Now, in EasyPower, this is going to be predominantly what we call a positive sequence or balanced simulation in the harmonics. We do allow you to use zero sequence, but in this case, I'll tell you that the capacitor banks inside EasyPower are all ungrounded. And so because of that, let me get some notes up here. Let me change to Microsoft Word. Because of that, these are the two predominant styles of banks that you can simulate inside the EasyPower software. One's going to be a Y ungrounded, and the other is going to be a delta connected capacitor bank. In both cases, we have series reactors in a set of 3. All right, now, oh, by the way, just wanted to let all of you know, I've written up a whole set of notes for this webinar presentation. I'm using them right now. I'm going over each of the pages as we go through this, but I'm going to PDF this and send it off to everyone, as well as a couple other odds and ends that I'll have for you. So you'll get a few more things. So let me minimize that now, and let's go back to EasyPower. And so the two main components are going to be the series inductors and the capacitor bank, either connected, Y ungrounded, or delta. And that data is specified here in the filter equipment data dialog. Now, if you want to, you could break these out as separate components. And I will just have to admit here on the inside of EasyPower, this filter wasn't necessarily put in here for designing. It was predominantly put in here just to simulate it. But if you're doing harmonic filter design, you actually want to see the actual voltage and conditions on this capacitor itself. And in that case, you may want to break it out. And if we were to open up another case here, let's see, we'll go here. In this case that I call distortion fix, you see that I actually have two examples of the same filter. And when we go to this case and start looking at it, you'll see that this filter here and this one here are identically the same. I chose to break out the components. So if you take a look here, it's 1.737 ohms with this resistance, which gives me an X over R of 50. And so I put in 1.737 and 50. Here we have the capacitor broken out as a 6 megabar bank, specified at 15.173 kV line to line. And this one is identically the same. So if we want to see the bus voltage here for any reason, we may need to break these components out when we're doing filter design. Okay, so impedance buffering is critical, and now let's look at the capacitor duty. Now, the quickest way for me to do that is to throw up my Word file again, and let's look down in this section on capacitor duty. These are the main criteria that we're going to be working with straight out of the ANSI Standard 18. These criteria are the RMS amps, fundamental kVAR, rated voltage, and the crest voltage on the capacitor. What I recommend doing is that when you're in a design for a harmonic filter, that you use the V root sum square, and I'll just, in a moment, I'll tell you the difference between RMS and root sum square off of the harmonic analysis. Use the kVAR that you see on the one line from the power flow results for fundamental kVAR. Use the root sum square voltage out of the harmonic analysis for your rated voltage. Looks, I made an error, didn't I? Let's retype these in again. This should be I root sum square, and this should be V root sum square. The rated crest voltage V sum, and we're going to talk about that in just a moment here. We'll be using that for looking at the rated crest voltage. Now, basically, each of these can be applied with straight looking at these limits, the 180% for the RMS amps, 135 fundamental kVAR, percent rated voltage 110. However, for the rated crest voltage, I had some discussions with an actual capacitor manufacturer who was involved in ANSI Standard 18. And what he recommended when you're doing designs is that you apply the rated crest voltage specification where this basically means 120% for an abnormal condition, and shoot for a rated crest voltage of 100% of normal conditions. So for instance, up here, I think this is, I actually discussed that right here in this section of notes. So what we want in our design is to basically make sure that when we're absorbing harmonic current in our notch filter, that the additional voltage rise, the peak voltage rise that we see across the capacitor, that we want to take that into consideration. What will happen is the peaks of each one of the waveforms. So we have the fundamental being our first one, and let's say we're absorbing predominantly fifth harmonic. The peak of that fifth harmonic voltage has the ability of being impressed in line, completely in line with the fundamental. Now, it may not be. It may be phased off a bit, okay? But we really don't want to play that game when we're rating equipment. So what we want to do is make sure that when the peak voltage of the fifth harmonic appears and it adds linearly with the peak voltage of our fundamental waveform, that we basically have taken that into consideration for the stress, the voltage stress going to be put on the capacitor. The capacitor is typically created by thin mylar, dielectric, or paper. And it's very thin, again. If it's mylar, it's typically impregnated with oil. And I'm speaking mostly about medium voltage capacitors. And so what happens is, since it's so thin, its main mode of failure is dielectric failure. And to make sure we cover for that, we take the rated voltage of the capacitor for whichever one we've selected, and we could go and do a square root of 2 factor and start adding up all the peak voltages, but you know, you can do it in RMS too. It's kind of the same thing. Or you can do it in per unit. You could do it in percent. But we need to make sure that we have taken that into consideration. And again, my recommendation for you is that for normal conditions, non-contingency conditions, that for normal operation, you operate it in 100% to have a conservative design. And for your contingency conditions, you're allowed to go up to 120%. We could probably break into just half hour of questions about, well, how long should that really be, you know, and everything. So just in your best engineering judgment, try to come up with all of your normal conditions having 100%. One last thing, capacitors are one of the most failure-prone pieces of equipment that we will apply. I remember doing a harmonic filter design for a large aluminum smelter, and we were going to be putting in 5 20 megavar harmonic filters. The failure rate, the published failure rate on the capacitor units basically said we were going to have 6 failures per year. I mean, that's a lot. I mean, the guys are going to be going out there, pulling a can out, de-energizing the filter, pulling a can out and putting it back in. Because of that, we specifically used smaller can sizes. So we didn't do 400 kVAR, which would have been nice to have done, but it would have been really difficult for them to get those out of the banks. And so what we chose was a smaller 200 kVAR so that at least they could possibly with the help of a small crane lifted out. The cans get really heavy the bigger they get, especially if they're oil impregnated. Okay, so these are the major items we're going to be looking at. V-sum. V-sum is a linear summing of all of the voltages. And what that does is it gives us an estimate of what the peak voltage stress is. We could basically increase everything by square root 2 and then divide it by a voltage that's peak voltage. It has a square root of 2 in it, but you don't really need to do that. You can divide it by the rated RMS voltage and get this percentage to come out for you. Now, the other thing that I said here was root sum square voltage on the capacitor. Root sum square voltage differs slightly from RMS in this way. It's the square root of the sum of the square of the harmonic components. Whereas RMS is really defined as an on the waveform quality or factor. And so when we calculate this, we're looking at a sine wave and calculating over one cycle, calculating our RMS value with all of the harmonic distortion in it. Here, we're just adding up each of the individual harmonics. If we have every harmonic component that's in this waveform that we're calculating RMS, these values will be identically the same. That's why we use root sum square, because when we're doing harmonic computations, we don't have a waveform. We're typically simulating each frequency independently when we're doing the harmonic computations. And so we have these numbers readily available, and it helps us calculate root sum square for voltage. Same thing goes for I root sum square. It's going to be the square root of the sum of the squares of all of the harmonic voltages, which will generate an RMS-like value given every harmonic you've simulated is really there. All right, now, fundamental kVAR. You will be getting that out of your power flow case. And so this brings up a really interesting point. That is, you need to be adept at moving back and forth between harmonics and power flow for getting your answers. One other very important thing, when you start applying power factor correction, which basically a notch harmonic filter is, it's a combination of power factor correction and filtering. What you're going to find is your voltage is going to go up. And so if your voltage goes up, you have to make sure that the size and the amount of power factor correction you're putting in there doesn't cause you to go into some form of an overvoltage condition. So make sure that you run power flow cases as well, and you'll see that with one of my examples that I have here. Okay, CAN unit ratings. Now, I've put a few of them in here for you. What I would recommend is that when you're making a notch harmonic filter is that you use as standard a rating as possible. I've seen a lot of European harmonic filter designs, and basically they're using really oddball, strange voltages, and because you can specify any kVAR rating that you want and any voltage that you want. But what I would recommend, so that in case you need units quickly, and you need to buy them because you've had more failures than you had spares to put back in, I'd recommend using some of these standard sizes, 50, 100, 150, 200, 300, or 400 kVAR, and just recognize the bigger they are, the heavier they are. Also, unit voltage ratings. We have a number of standard ones. I pulled these out of I think I pulled this out of the GE handbook, I believe, getting all these standard voltages with their basic impulse level as well. So you can see we have a whole range that we can select from. Often harmonic filters, which are connected Y, ungrounded, you'll be using a line to neutral type voltage specification, and you'll often be in this 8320, 8760, 9540 range, typically. I have an example that we're going to be looking at in just a minute. Okay, one of the things that will happen, and let me switch this over to EasyPower again, in your systems, when you have a harmonic filter application on the bus. And so I have this distortion fix example. It's very similar. The only thing I've added to this is I've got some harmonic load down here so I can get some distortion. When I go to harmonics focus, When I run my impedance scan, obviously I get a ramp because I don't have anything on. Then, if I put one of these filters on, I get a tuned fifth harmonic filter. One of the most important aspects to recognize here is the first parallel resonant point. Basically, every time you have a combination of inductance and capacitance in any form, whether it's just because of a capacitor bank on the bus or because you have a filter on the bus, it's like one of those balloons, you know, that the clown ties up. Okay, so just you're holding that tubular balloon. If you pinch it, it's going to make the rest of the balloon expand. That's exactly what we're doing with a harmonic filter. Every time you have a filter put on a bus of some form, you're going to be pinching it down to a filter point, and it's going to manifest or react to that and create a first parallel resonant point below the filter. So for this fifth harmonic filter, we have a first parallel resonant point, which in my opinion is not really in a very good place. I would recommend that you position this away from the third harmonic. In fact, my recommendation for anyone doing notch harmonic filter design is, if you have the ability to, move it away from an integer harmonic. Put the first parallel resonant point in between integer harmonics if you can. Now, when I say if you can, the reason why is the first parallel resonant point is completely dependent upon two things: the system short circuit strength at the bus where the filter is being applied, and the size of the bank. Those are the two key factors. In fact, let me load in, let me bring back Microsoft Word here. And let's scroll down to a picture that I have right here. Okay. So in this picture, what we see is, let me make this a little wider. We can zoom in a little more. In this picture, what we see is, for a location at a bus remaining constant, in other words, the transformer is the same and it's not changing, the main upstream supply transformer. As we decrease our bank size, look at where the first parallel resonant point goes. So the larger your bank, the lower you push it. The smaller your bank, the higher you push it. Another thing you can recognize here as well, and this is a key point when you're doing harmonic filter design and you're choosing to lump into a total single fifth filter versus a 5 and a 7, okay, is that the larger the bank, the broader the filter point. The smaller the bank, the narrower the filter point. If we had this, let's say this was one of our filters that we had designed. If we had this small 0.2 megavar filter on, and it was composed of, you know, obviously we probably couldn't use much over 50 kVAR cans or something. When you blow one of the cans, you're going to shift everything to the right. And so one of the key points for notch harmonic filter design is making sure it's broad enough so that when this resonant point or the filter point shifts a little higher, like maybe to 5.1 or something, that where this point moves does not get into a bad area. So obviously we could shift way even up to the 6th harmonic or so, or 7th, and this first parallel resonant point is not going to sit on the 5th, and that's a good thing. The smaller the bank size, the more you risk that being an issue. And that brings up another point. That's why we typically slightly detune our filters. So when I'm saying 5th harmonic filter, in almost every case, it's going to be somewhere between 4.7 and 4.9 in its tuning, for the key reason that if I ever blow units in it and it starts shifting upwards, I basically can keep this first parallel resonant point from hitting right on the 5th harmonic, because if it did, that is not a good condition that you want to have happening in your facility. There's a ton more details that I could say on that, about how you have to make sure that you also include things like blown can protection. I just didn't have time for that to put that in here. So we've looked at slightly detuning the filter for this first parallel resonant point. We looked at how it changes. And another thing that I want to mention real quickly is that do not ever, please do not ever, blend bare capacitors on a bus with a filter, because you really haven't fixed anything. You've just moved it to another problematic location. In this case, this first parallel resonant point before with this bare capacitor on the bus was really down here someplace in a problem area, like between the 5 and the 7. When you apply the fifth harmonic filter, you pinch the driving point impedance where you filtered, yes, but you end up just shoving and moving the parallel resonant point from that other capacitor that's on the bus up to a different location. So you're not really solving anything, you're just moving it. And again, if this happened to be sitting right on the 11th or the 7th where you have predominant harmonic content, you're just going to have an issue. There is a whole bunch of words we could go and talk about harmonic filters and why we choose a larger fifth versus a 5, 7, and 11. Often the reason why is because we want to avoid this condition. What happens is when you supply, in this case I have a 3, a 5, and a 7, okay? Notice that the filter point is not as broad. So as we saw, smaller bank sizes, narrower filter point. And again, all you have to have is a slight amount of shift in these parallel resonant points between these, and then you're going to have a problematic condition. This also, basically what happens is, you can see that this doesn't necessarily go all the way down to zero impedance here. The smaller you break this up into pieces, making 3, 5, 7, 11, and 13, you could break this up a bunch if you wanted to, you'll find that you're not going to filter as effectively each one of those harmonics. So we are at 10:38. I've got a couple more minutes to look at a few more items, and then we'll hit some questions. One other item that I want to discuss here is what is called inter-filter resonance. And this is a rather unknown thing. And I remember back being at PTI, and Ray Stratford would always say, oh, you got to be careful. If you put two filters on the same bus, they can talk to each other. And so you really want to be careful not to put two filters on the same bus. Well, interestingly, I actually ran across this condition at a chlor-alkali facility. And they were doing maintenance, and they had two separate buses with two separate fifth harmonic filters that rarely were connected together. Because of, maybe a little bit of being a little sloppy in the maintenance procedure, or just only, having certain spares on hand, they didn't put back in the right size capacitor units in one of the filters that had a few failed units. They put smaller ones. And so what happened was they created a condition where they had one filter properly tuned around the 4.9 or something like that. And then the other filter, because it had less kVAR in it, the tuning point had gone up. And these were connected onto the same bus. What happens is you end up with the parallel resonant point between the two, just like you would between a 5 and a 7, just like we showed right up here. It's just that it's really, really close together. This may not seem like much of a big deal, but until you realize that, it's centered right on the fifth harmonic, which is the point that you are trying to filter. The other thing that you can see and discern if you run a few simulations is it causes a resonant condition between the two filters, and their RMS amps double or quadruple. And this is exactly what we saw. I saw a cast in concrete current limiting reactor, which was the reactor for the filter, basically it was almost red hot. It was really cooking. So if I go back to EasyPower, and I have a case that I can load to show us. If I go to desktop on webinar and interfilter resonance, I have this case here. So let's go into EasyPower Harmonics. Let's put both of these off. Let me spread this out a bit. And I'm going to put both of these right on the bus, and I'm doing a driving point impedance scan. And I zoomed in. I ran my scan in the harmonic options from 4.7 to 5.3, and I show it's at right here at 5. Now, what's interesting, okay, I'm making that happen. If you do a distortion, let's put one filter on. You do a distortion, you're at 2.7 with one on. Without it, it's around 9 or something for the harmonic load I have. So with one filter, I got down to 2.7. I put two filters on. Ooh, it goes up, right? Well, it actually didn't go up that severe. And so you might be thinking, oh, well, that's really not that big a deal, until you look at the current in each of the filters. Okay, this is, I decided just on purpose, I'm showing the root sum square current into each of these filters. Look what it is for one, 220. Okay, so if I put this filter online, it really should be 220. I mean, they should be drawing about the same amount of current. Maybe they would even be sharing some of the fifth harmonic, okay? So it probably might even drop a little bit. But what happens is when you put them on the same bus together, it like quadruples. And I've seen this and I've measured it. Amazingly, we went out there, switched the filter off, put the right size capacitor units in it. Bingo, the problem went away. All the currents dropped. So this is a real condition that you can actually experience out in the world. Okay, I haven't seen any questions appear yet in the chat box, and it's 10:43. So let me see if there's anything else I want to look at quickly. We've got interferential resonance case. Let's look at this case here, this distortion case. Just wanted to show you where I have this broken out and where I have the single filter. If I do a frequency scan, and let me bring the plot up, I get exactly the same result. So here's our first parallel resonance sitting right about the third, which is not a good place. And then here we're tuned about the 4.8 or so. And if I were to use this one, broken out into separate components, I can get identically the same simulation, about the 4.8 harmonic sitting right on the third. So these are completely comparable with each other, these two modes. If you want to break it out into separate components, you can. If you want a single component, you can do that as well. In this case, if I do a summation calculation for my distortion, notice that I'm plotting root sum square voltage here. Okay, let's look at VTHD first and ITHD. So the distortion on the bus is 9.6% without the filter. I put the filter on. Voila, we can drop it down to 2.9% voltage distortion. So I've simulated 3 6-pulse drives here, and I've put in a fifth harmonic filter. Obviously, I don't have any third appearing. So, so that was a good design. Okay, well, we're into the question answer, and let me unmute everyone. And I see the first question from John McQuilkin. The standard 2002's limit for current was changed from 180 to 135. Please see the email I sent you. Great, thank you very much. Yes, if you look in my notes, I see probably said I had not updated that. So in my notes, I think I noted 1980 or something like that. Did I say that? No, but I had it in there before. I must have accidentally deleted that out. Thanks, John, very much for that update. So I'll change this for everyone for the RMS amps to 135%. Any more questions?
Can you hear me or no?
Yes, I can.
Could you share some of these little harmonic example studies that you have so we could fiddle with them and see how all the values interact?
Yes, absolutely. In fact, I'm putting these notes together into a PDF form, and all the cases, and on top of it, something I didn't get a chance to go to yet, but let me show you now something that I will supply for you.
Okay.
This is my own, let me load up Excel. This is my own filter design program that I will let you have. This is, it's used at your own risk. Okay, you have to check all the numbers yourself. But I use this on the side myself so that I can specify a tuning point and generate the actual amount of VARs to put on at CAN rating, the voltage rating, and then also the ohms per phase for my reactor based on actual capacitor units rather than specifying a total sum kVAR.
Oh, wow. Nice.
Yeah, so I'll supply this to everyone. On top of it, a couple other things if you look in this spreadsheet. Looking at the reactor taps, you see, there's reactor taps specified here, and you can see I have tolerance checks here. So I spec'd capacitor reactor tolerance of 3%, 3%, and then you can see how the tuning point changes based on tolerance differences. Okay? One other thing that I put in here is called a blown can tuning check. So what I do is I see how my resonant point shifts when I blow 1, 2, or 3 cans. And what this allows me to do is use this to determine, hey, if I have 2 blown cans, I'll simulate an unbalanced system and I'll see where the neutral offset is for an ungrounded Y bank. Thus, I can apply protection and determine a setting for it. Also, in this spreadsheet down here, I have a capacitor bank functional specification listed here the way I've done it for the last 20 or so years, and the reactor functional specification as well. And on top of it, this actually has a quick harmonic simulation in it based on a single short circuit impedance driving MVA. This is done all with reactance. There's no resistance put in here. And so you specify an MVA short circuit, system-based frequency, tuning point, your capacitor, and then you put in some spectral content here, and it'll generate the answers for you. Any other questions? Wow, it's quiet out there. Okay. Well, let me see, since there's no questions, let me see if there's something else I'd like to do a quick talk over. I noted that one of the key items is using the filter for power factor correction at the same time. And you're going to have to play with the amount of power factor correction that you need versus your first parallel resonant point. Remember, we discussed that the first parallel resonant point changes depending upon how big your size is of your capacitor bank and also what the upstream short circuit impedance is. And so we have to balance those back and forth. So you may right out of the gate say, oh, well, I need X amount of power factor correction. And that's good, but you need to perform simulations and do frequency scans with that design hooked onto the bus to make sure you're not sitting at an integer harmonic for almost all of your normal conditions. Okay, so I got a question here from Jedson. Have you had any issue with short circuit ratings of the capacitor switches? Okay. Interesting question. Are you talking about the switches that are just used for disconnecting and grounding? Pardon me?
So I think it's fine.
Oh, are you talking about the breakers that are being used for application?
But I don't know that we necessarily do anything.
Okay. I haven't gotten a response yet. Now, one of the things about harmonic filters that you don't have to have a real concern for, and that is what's called back-to-back switching. Often if you have two capacitor banks located near each other, you have to include some type of a surge protection, a reactor in the circuit, so that when you hook one up to the other, that it doesn't dump all of its energy in and basically cause a condition. And so for back-to-back switching, the reactors in the filters themselves help you. Talking about the switches for the individual cans. Okay, my recommendation for the individual cans is that, I mean, in all the filters that I've designed, there aren't switches on them. There's individual fuses. And my recommendation would be that for your filter applications, whether they're metal enclosed and they're in an enclosure or whether they're outdoor stack rack, in either case that you have individual fusing on each capacitor unit. I know there is a trend in some filter applications to use internal fuses. I know that they're there in certain cases. In my recommendation, I want to see that it's open. I want to see an open condition. And so that's why I've always preferred the external fusing. And the only switches that I'm available or that I'm aware of that are on, in capacitor filter banks is going to be like a switch that opens, but you have, for grounding. In other words, you're in an energized condition, then it goes to a middle condition where it's not connected to anything, and then you ground it for safety reasons. You have to have a real upstream breaker to open and close your filter. Any other questions? Or did I do a good job on that one? So have any of you seen filter capacitor banks where there's several stages, maybe hooked in a binary configuration, where you can throw some on and take some off so that you're matching power factor more closely? In those conditions, I have seen times where for those type of arrangements there's vacuum bottle failures, and I think I've seen it mostly for just plain capacitors being applied on a bus. And so remember, for every capacitor that you put on the bus, as you're changing it, if you're switching on more capacitance, you'll find that your resonant point is shifting all the time. So if you're going to do a staged bank of any kind, believe it or not, you're going to really need to test it for each one of those stages. If you're going to put in filters, remember, you do a staged bank with filters, you have to have a set of 3 reactors for every single one of those stages. So your cost is going to be going up dramatically. And that is the reason why we typically apply fairly large size single tune banks for that reason, because when you're doing a lot of switching of banks, you got all the additional reactor costs, you're going to have all the vacuum bottle costs for switching. And the other reason is, believe it or not, but if you apply a 5th harmonic filter, it will absorb 7th. It will absorb 11th. So it's not just filtering only 5th out of the system. Remember, it's current division. And so if we were to look at this distortion case here that I've got running here, if I were to look at, without the filter, if I were to look at the current going up through the transformer in this bar plot, I've got 5, 7, 11, 13, etc. Now, if I put this filter online, and then I look at, for instance, the current going into the filter, what I'll see is, yes, I'm absorbing a lot of 5th, but I'm absorbing some 7th and some 11th and some 13th. If I now look at the current going through the transformer, I'll see that, most of the 5th, now let me scoot this scale up a little bit. So 0.2 maybe. So most of the fifth has been absorbed, because the fifth was up here, but most of it's being absorbed by the filter, but it's still doing current division. Some of the fifth is still getting out slightly, and then there's your 7, 11, and your 13. But the filter itself will absorb some of the higher frequency harmonics when you apply it. And that comes into play when you specify it. So if we go back to this spreadsheet, you notice down here for the reactor functional specification, I didn't list just fifth harmonic flowing into this reactor. I put all of the harmonics that I saw in my simulations that this would be absorbing, and I put those here in my filter duty for my reactor requirement for amps and volts across the reactor. Volts, this doesn't even hardly need to be here, really. It's really key. The key thing is amps for your tuning reactor. Any more questions? Notice here I put taps specified. I've had several cases where, because capacitors now are typically 10%, their tolerances are 10%. Now, capacitors always come in a positive tolerance, okay? And when they're in that positive tolerance range, you'll find that your kVAR is going up significantly. I had a condition where, after designing and having an install on a harmonic filter, during the commissioning effort, we actually pulled capacitor units out of it because, on average, after measurements, I discovered this, the tolerance was about 7% high on the entire bank. I pulled out an entire row of capacitors. It was 3 of them, one per phase. I pulled out an entire row of them to basically bring the filter back into the same range that it had been designed for, which reduced the current loading on the reactors back into, their nominal range. So that's one thing you may want to watch, is that when you get these things actually out there in the field and built, the capacitors will be significantly greater than 3%. Almost nobody will build you a filter with a 3% capacitor anymore. When we were doing this a number of years ago, Ray Stratford had connections where he could force people to hand-pick units that were not any greater than 3% higher on their kVARs. But these days, I see them coming out between 5 to 7 to 8% high. And in that case, there's 2 ways to correct for that higher kVAR for your filter tuning point. Number 1, pulling capacitor units out. Number 2, changing the tap on the reactor. So that's why, for myself, when I put out a specification, I always have reactor tap specified. Well, I thank you very much for attending, and I hope all of you have a really great week.